So the first way that we multiply vectors together is the easiest to understand. That's this lesson. And it is basically taking a vector and multiplying by a scalar. A scalar is a number, just a number, no direction, right? So multiplying by a scalar just means we take a vector and we multiply it by a number, essentially. And what that does is if your vector is pointed in space like this marker, pointed off in this direction, let's say with a certain magnitude and direction, if we multiply it by 2, then what it does is it makes the length of the vector double the length, double the magnitude, but the direction of it stays the same, okay? That's intuitively what's happening. You know, a good example of that would be if I tell you that the wind is blowing this way at 5 meters per second, that's a vector, right? It has magnitude and it has a direction. The direction of the wind is this way, okay? Now, if I tell you that on Tuesday, the next day, I have 5 times the wind speed or the wind velocity, what are you going to think about? You're going to think it's blowing in the same direction, but 5 times stronger. So if it was going 5 meters per second, initially it's going now 25 meters per second. That makes the vector arrow 5 times longer, but in the same direction. We're multiplying in that case by a scalar, by a number. And that number just stretches the arrow out, or it could shrink it if you multiply by a fraction, like multiplying by a half or something. But it maintains the same direction. So that is the big picture that we're doing in this lesson. But keep in mind, in future lessons, we have to multiply a vector times another vector. And that gets a little more involved because there are different ways to do it, and it depends on the physics of what is happening. So for now, just focus on taking a vector, multiplying by a number, which essentially makes the arrow longer or shorter, but you maintain the same direction. So let's jump into a concrete example. Instead of, you know, just kind of like talking about it, let's do a concrete example. What I'm going to do is superimpose these vectors on an XY plane so that there's absolutely no confusion about what's going on. Here's the x-axis, here's the y-axis. I have a vector, and here is the 1 tick mark, here is the 2 tick mark. I have a vector which points in the up direction directly on the y-axis. It starts at the origin, here's 1 unit, here's 2 units. What is the name of this vector? The name of this vector is what we call a vector. I'm just going to name it vector A. Right, what I want to do is I want to take this, and I want to take this A vector and multiply it by 2. So you write it just like in algebra, 2 times whatever you're multiplying by. In this case, it's not the variable A, it's vector A. That has the arrowhead on top. But when I multiply by 2A, what am I doing? I'm taking 2 and I'm multiplying by what the vector is. But look at what I have here. What is this vector? Well, it's pointed straight in the y direction, no x component. And here is 1 and here's 2 tick marks. So this vector in unit vector notation is 2 in the j direction. Because remember, I hat is in the x direction, j hat is in the y direction, k hat is in the z direction. This vector points only along y, 2 units long, so it's 2 in the unit vector y direction, so that's pointed 2 units up along y. We're taking this vector A and we're multiplying by 2. So when we do that, what do we get? I'm telling you, you know, without proof, that this is what basically happens. You treat it just like algebra. Just like algebra. You multiply the coefficients, the numbers, and the unit vector just stays along for the ride. If you were to go back to algebra and replace this funny looking unit vector with a variable x, 2 times 2x, what would you get? You would have 4x. And so we're replacing, I'm using that as an analogy because the unit vector is not a variable, but it behaves the same way. It's like an object. What you have here is 2 little objects that point up 1 unit each for a total of 2 units in the up direction. And when you double that, then finally you have 4 times the little unit vectors pointed up. So when you multiply a vector times a number, what you end up doing is multiplying the numbers, and you keep the unit vectors, they just come along for the ride like variables, like regular multiplication. Now, what would something like this look like if we actually plot it? Well, we'll draw a little xy axis here. And this is 4 units in the up direction. So it would be 1, 2, 3, 4. And this vector would be this vector pointed up like this. And this is 2a vector. Now, just to make sure you totally understand, what is the a vector equal to? It's 2j, like this. And we were just plotting 2 times a, which is 4j. Like this. So what we did, you see, is we started with a vector that was 2 units long, a magnitude of 2 pointed straight up, And once we multiply by 2, we get a new vector, which is 4 units tall, again in the same direction. If you look at before and after, multiplying the vector by 2, going from this picture to this picture, just takes the arrow, doubles the length, which is what we get, and it's pointed in the same direction. This process holds for multiplying any vector in any direction by a scalar, which is just multiplying by a number. When you multiply by a number, what it does is it multiplies the length of the magnitude of the vector, but you maintain the same direction. So if this were representing, for instance, a velocity of, a velocity going north, like a wind speed or a current in the river or something like this vector represents some velocity up. Doubling the velocity, it maintains the same direction of the flow of whatever it is, but it makes it double the speed in that direction. Or if this represents a magnetic field pointed up, then doubling that magnetic field just makes it stronger, but it's still pointed in the up direction. I'm harping on this because I want you to remember instead of trying to think about, well, what makes sense? I want you to remember multiplying by a number maintains the direction, but just changes the length of the arrow, right? And likewise, if I had multiplied this by 1/2, instead of 2a, I multiply 1/2 of a, then what would happen is 1/2 of 2 is 1, and you would have a unit vector pointed up with a length of 1. It would cut the arrow down by half in the same direction. Now let's do a similar situation. Underneath here, I'm going to draw another xy coordinate plane here. And by the way, before I get too far into this, I want to tell you that I'm going to give you physical significance in just a minute of why we actually take vectors and multiply by numbers. I don't want you to wait 5 chapters in the future to figure out why we use this stuff. So if you just stick with me till the end, you will learn not only how to multiply vectors like this, but what we use it for. We're going to talk about Newton's law here in a second, one of Newton's laws. And then we're also going to get practice solving problems and just really getting comfortable with what's happening here. So let's say I have a new vector. And this vector is 1, 2, 3 units pointed strictly along the x direction like this. This vector I call b vector. And how would I write this vector? It would be 3i. Because remember, I hat means unit vector in the x direction. 3 of these guys means the arrow points 3 units like this. Now, what if I want to take and multiply 3 times vector b? Well, I would be multiplying vector b, which is 3i. And so 3 times vector b is what? What is the rule? We multiply the numbers, and the unit vector just comes along just like a variable would. And so the answer would be 9 times i. You can see it's going to be 3 times the length of the original vector pointed in the same exact direction. So I will try to draw that, but I'm going to have to stretch my x-axis out to do it. So I'm going to do it something like this. So this is still x, and this is still y. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 9 right there. And then this vector would be pointed something like this in the x direction, and I would call it 3 times the b vector, which is 9i. So you see, the same exact rule holds. The vector has completely changed direction, but the same rule holds. You take the original vector, when you multiply by a scalar, what it does is it lengthens the magnitude or the length of the arrow, the magnitude of the vector. How much? 3 times the original length. And the direction of the vector remains unchanged. So if this represents wind speed, and on another day it's 3 times the original wind speed, then the direction is maintained, but the speed itself is 3 times longer. That's represented by an arrow 3 times longer. Now, so far, I picked simple examples so that it's very easy to visualize. If you have a vector in the y direction, you multiply by a scalar, it stretches it, or it shrinks it if you multiply by a fraction. In the x direction, when multiplying by a number, it either stretches it or shrinks it if you multiply by a fraction. And so in the x and y direction, makes sense. Now what happens if the vector is actually not pointed in the x or the y direction? What if it's pointed in some angle direction? What do you think is going to happen? Just take a guess. Well, if it was pointed at some angle and I multiply by 4, then the angle will be maintained, but it will be making the arrow 4 times longer, which means 4 times the magnitude, 4 times the wind speed, or 4 times the magnetic field, or 4 times the acceleration, or whatever it is that I'm talking about, but I maintain the same direction. So let's just make sure we understand that. All right, let's say that I have some vector pointed in this direction. I'll make it about this long, right? And I'm going to call this C vector. Now this C vector, I'm not going to put an xy axis to it yet, but it forms some angle with some local x-axis right here, right? If I take some C vector and I multiply it by 4, right? 4 times the original C vector, and the original vector pointed at some angle like this, then what do you think it's going to look like? Well, it's going to be basically starting from some local starting point. It's going to be, let me go maybe a little bit over here, something like this. It'll be 1, then 2, then 3, then 4. I'm putting the little marks here to help me gauge the length of the thing. This is supposed to be 4 times the length of the arrow, but again, at the same angle. You can see that these angles are basically the same. The only difference is this was 4 times longer, right? Right? And I think I mentioned this verbally, but what if over here I start with a vector? Let's make it this long. Let's call it D vector. And let's make it like this. So it's 3 units long. It points it in this direction. And how would I identify this direction? It would be some angle right here. So this is 90 degrees. This is a little bit bigger than 90 degrees, some obtuse angle like that. And what if I took this vector, and what if I shrunk it by multiplying by 1/3 of the original vector D? What's that going to do? It's going to maintain the same exact direction, but it's going to be 1/3 of its original length. So it's going to be up like this, only 1/3 of its original length, but again, the angle is going to be maintained. So same exact angle. So this goes like this. So intuitively, I'm hoping by now that you understand that no matter what the math is doing, physically what is happening, when you multiply a vector by a scalar, you stretch the length of the arrow, maintain the same direction. And if you multiply by, instead of a number bigger than 1, smaller than 1, it shrinks the vector. So now that we understand the basic idea about what's happening when we multiply a vector by a scalar by a number, let's take just a little, I don't want to call it a detour, but a little bit of a side story to talk about why we care about this. Why are we doing this in physics? And then once we do that, we'll solve some problems and we'll wrap up the lesson with a kind of a little bit of a proof at the end of the lesson, which is very important. Believe me, I wouldn't waste my time talking about it if I didn't think it was really important. So in physics, we multiply vectors all the time. I mean, most equations in physics are actually what we call vector equations. A vector equation sounds complex, but it's not. It just means that the equation involves vectors. Because most things in real life, I should say most, but a lot of quantities in real life are vector quantities. Velocity, anytime you throw a ball, it's a vector, it has a direction. Anytime you push with a force, that has a direction, that means it's a vector. Magnetic fields have direction, electric fields have direction. So they're vector quantities. And so any equations involving magnetic fields or forces or velocities or even accelerations or displacements, because those quantities are vectors, then the equations are vector equations. And anytime you multiply things, then you have to know how to deal with multiplying those vectors. So the most famous example of multiplying a vector by a scalar like that is the famous Newton's second law of motion. So F equals ma. Now, we haven't gotten to this yet, okay, so I had to make a little bit of a choice here. I could either not tell you about this and just wait a couple chapters till we cover forces, but that would be robbing you because I think most people can understand this and a lot of people have even seen it before, okay? So this equation is very simple to understand. Here, m is any massive body, anything that has mass in kilograms. When you push on it with a force, that's what or pull on it with a force, it produces an acceleration in the object, right? So forces in physics, we're going to learn a lot more later when we talk about it. They cause things to accelerate, to change their motion. Forces don't really cause motion per se, because if you go into space and you grab a ball and throw it, then the ball is coasting forever and ever and ever with no outside forces anymore. So forces are not required to maintain motion. I mean, you know that. Just think of deep space. Throw a ball in space and it moves forever with no additional force. I don't need a rocket thruster to keep the ball moving. The motion likes to always happen. That's another one of Newton's laws. But what forces do cause is for the motion to change, which we call acceleration. If I have a brick in space and it's moving very fast, the only way I can change its motion is by applying a force. If I apply a force, then I cause it to accelerate. So when we talk about this situation, when we have forces, we say that they cause accelerations, right? So you can think of it as here is an object, right? And this object, I'm drawing it as a point, but it has some mass. So I'm going to say that this little dot has some mass. And what I'm basically saying here is that whenever I apply some force, let me draw this as some vector here that is a force, then what happens as a result of that force is it causes this object to either speed up, basically to accelerate in the same direction as the force is applied. So basically here you might have some acceleration vector. So these guys are lined up in the same direction. Now I want you to compare the situation to what we have over here. If we have a vector multiplied by a number, it produces another vector, same direction, just different length. If we have a vector here multiplied by a number, then it produces a new vector, which is either longer or shorter, but in the same direction. Here I'm telling you that we have a force vector, and then we're basically a force vector here multiplied by a number, and it produces or has corresponding to it another vector, which is either longer than shorter than it, and so they're pointed in the same direction. And this is because when you see this equation in a lower level class, like maybe a high school class or even lower than that, then you're just told F equals ma. The actual equation for this is not quite like this. The way you write it in vector form is force vector is equal to mass times acceleration vector. This is what we call a vector equation. Because force is a vector, it has direction and magnitude. Acceleration is a vector, it has direction and magnitude. And mass is not a vector. Mass is a scalar. If I have an apple that's like, whatever mass of the apple is, that does not have any direction, it's just a number. So what you're doing is you're taking the acceleration of the object, you're multiplying by the number. And what do you get? You get a new vector, which is just going to be either longer or shorter than the one you were multiplying by. If the mass is a very big number, then like bigger than 1, then the force vector will be longer, okay, because it'll require more of a force, in other words, to make that acceleration happen. If you're multiplying by a mass that's a very small mass, maybe some fraction of a gram or something like that, then you're going to cut this vector down and the force vector will be smaller, meaning you'll need less of a force to produce the same acceleration if the mass is smaller, okay? So you can almost think of force and acceleration being two vectors, well, you can think of them being two vectors pointed in exactly the same direction. The vector arrows on top are telling you they're vectors. The vectors are, one vector is multiplied by a scalar, so now knowing what happens when you multiply by a scalar, you know that these two vectors have to be in the same direction, just like all of the examples that we showed on the board. So this is not a lesson in Newton's second law, but you can understand a lot about how this works by having a concrete idea in your head, a concrete example. So when you think, what do I use multiplying a vector by a scalar for? You should be thinking Newton's law, because that is a vector multiplied by a scalar. The answer to it is a new vector pointing in the same direction, and this vector will be either longer or shorter depending on the value of this number, the mass. Big mass, small mass changes how the arrows are how long they are, but they're always pointed in the same direction, just like our examples there. All right, that's why I tried to draw these guys in the same direction. Now I've drawn it here where the force vector is smaller than the acceleration vector, but depending on the value of m, it might be longer or shorter, just depending on the exact problem that you have. All right, now the next thing I want to do before we get any farther in this is I think it's a good point to actually solve a real problem. Now, a real problem here is not going to be a very complex situation. It's not going to be a very complex problem, but it's still good to get familiar with what we're doing. The problem says a vector d pointing northward has a magnitude of 2.5 meters. So this must be some sort of displacement vector. Find the magnitudes and directions of the following two vectors. The first one is 4 times d, and the next one is -3 times d. So it's possible to take a vector and multiply it by a negative number too. You can multiply a vector by a positive number, by a negative number, or by any fraction. You can multiply a vector by any number you want. Let's see what happens in this situation. So first, let's draw a picture, because that's what we need to do. I think pictures are good. You don't have to do it, but let's, actually, instead of drawing the picture first, let's not do that. Let's just say that d vector, it says it points northward with a magnitude of 2.5. So if you envision it pointing upward, then you know it has to be 2.5 in the j direction, because x is in the I direction and j is in the y direction. So this is a northward pointing vector. So for problem A, what you're trying to figure out is what is 4 times d vector? Well, it's going to be 4 multiplied by d vector, which we now know is 2.5 in the j direction, right? And so 4 d vector is, what's 4 times 2.5? It's 10 in the j direction. So this is the answer, 4 times d. All right? Now let's go and do the next part of the problem. Then we're going to draw a picture to make sure we understand. If we take this same vector and multiply it by -3 times d vector, what do we get? We get -3 times this, which is 2.5 j. And so what do? We already know that when we multiply vectors, we just multiply the numbers. The fact that this is negative has nothing to do with it. We still follow the rules of math. So what we have here is 3 times, or -3 times 2.5 is -7.5 in the j direction. And so this is the answer to the problem. So you see how we were able to do it without drawing any pictures. We follow the rules of math. When we have a vector, we multiply by a scalar, we just multiply the numbers, the unit vector comes along for the ride. We're multiplying by -3, we still follow the rules of math. The answer is a negative number in front of the unit vector in the j direction. Now let's see if this makes any sense at all. What we'll do is draw a little coordinate axis right here, x and y. And the first thing I want to do is I want to attempt to draw what the original vector is. So what I'll say is this is 2.5 in the north direction. I'll put a little arrow right here, and I'm going to say that this is d vector. And what it is equal to is 2.5 in the j direction, because it's pointed straight up northward, right? So I could put tick marks, 1, 2, 2.5, 3, and so on, but I'm just basically showing 2.5 right there. Now what we're saying is that 4 times d is a vector pointing 10 units up in the j direction, all right? 4 units up in the j direction. So what I can say is that this vector, 4 times d, is there's 1, there's 2, there's 3. This is even going to be taller than this. Here's number 2, here's 3. It's going to be way up here, actually. I should have probably drawn the vector, I think, or the original vector a little bit smaller, but that's okay. We'll get it done. Let's go up here. Okay? So if this is 1 unit, then this would be 2 units, and this would be 3 units, and this would be four lengths of the original vector, essentially. Means that this new vector is going to point all the way up here, and this is the 10 mark right here. And so this vector is 4 times d, which is 10 in the j direction. So if I put tick marks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then this vector would be at the 10 mark, and this vector would be exactly at the 2.5 mark. And you can see that it's 4 times bigger in the same exact, or 4 times longer in exactly the same direction, like this. And so if you wanted to write it down in terms of north, south, east, west, you could say that this vector is, I guess I put in parentheses, 10 meters north, pointed north, because the original vector was 2.5 meters pointed north. So this vector, you write it in vector notation as 10 in the j hat direction, which is 10 meters in the north direction. All right, now what does this one represent? When you multiply it by a negative number, you get a negative 7.5 down here. So if we go down here and say, all right, if this is negative 2.5, and then this would be negative 5, and this would be negative 7.5 down here, then this vector is pointed down here like this, and the negative 3 times d vector is negative 7.5 in the j direction, down like this. So notice that this one is 3 times longer, but in the opposite direction, because when you multiply by a -1, it takes and it flips that thing around, and then you stretch it. So you can kind of think about it as multiplying by the negative sign is what flips the vector around, then multiplying by the 3 stretches it out in the negative direction, so you have negative 7.5 in that negative direction. So if you wanted to write it in terms of words, you would say that this was equal to 7.5 meters south. But mathematically, we write it like this because the direction information is contained here. The j hat direction is positive, so the negative 7.5 j hat means negative 7.5 units in the down direction. So we have done basic examples with vectors pointed in the y directions, vectors pointed in the x direction. We talked a little bit about vectors that are slanted. We talked a little bit about f equals ma, which is an example of taking a vector and multiplying by a scalar, which is a number, to produce a new vector. And then we did an actual example multiplying and so on. What I want to do to close it out is I want to close the loop with you a little bit. What I want to do is focus a little bit on these angled situations. What if you have a vector at an angle can we prove to ourselves that if a vector is at an angle, I told you that when you multiply by a number, it's going to stretch it or shrink it, but it'll maintain directions. Let's prove that to ourselves so that we absolutely understand what's going on. And it's not hard to prove. So let's go ahead and do that. Let's say that we have a vector, and I'm going to put it on the xy plane like this. And let's say that this vector, I'm choosing these numbers carefully. Here's 1, 2, 3, 4 units, 1, 2, 3 units. So here's 3 and here's 4. And what I'm going to do is draw a vector where the tip is right there. So here is the vector right there. What is this vector? We're going to call it vector A. And what is this vector in unit vector? It's 4i plus 3j. So 4 units in the x direction and 3 units in the y direction. So that's vector A there. All right. Now I've told you what happens if you actually multiply this vector A by a number. Let's multiply A by 10. So what we're going to do is take this vector and multiply it by 10. So if this represents some velocity of the air, then if we multiply it by 10, then the velocity is 10 times faster, but pointed in the same exact angle direction as this guy right here. So let's see if this is what we get. We would get 10 and then times the A vector, 4i plus 3j, right? And so if we do this, we multiply it in, we distribute it in, what do we get? 40i plus the 10 times 3 is 30j. So 10 times vector A, in unit vector notation, gives us this. Now let's plot this and see what it actually looks like. Okay, so what we'll do is we will draw this guy right here, like this. Now I'm cheating a little bit because you see my tick marks, I only had 4 tick marks. If I tried to make 40 tick marks, they would be really small or I would need to do a bigger board. But what I'm going to do is draw this guy out to here. I'm going to say this is 40 units long, and I'm going to say this is 30 units long. And so what you can convince yourself is you have an arrow going right here. This is what the thing looks like. This is 10 times vector A. It's 40 units long in the x direction and 30 units long in the y direction, because when we multiply this thing and we distribute it in, and we're multiplying each of the components by 10. In other words, we're stretching the x component of the original vector tenfold, and we're also stretching the y component of the original vector tenfold. So we get x and y components which are 10 times bigger, and so of course the vector is now in the same exact direction, but it's 10 times longer. Because, let me say one more time, because you've stretched the x component tenfold and you've also stretched the y component tenfold, it makes the slanted length of the thing 10 times bigger, but pointed in exactly the same direction, because the ratio of the x and the y components is the same as it was in the original problem, because you're multiplying each component there. Now let's prove it to ourselves even further. Let's go down below here. What is the magnitude of vector A? It's the square root over here of 4 squared plus 3 squared, which is the magnitude. This is 16 and this is 9. So 16 and 9 is 25. And when you take the square root of 25, what do you get? You get 5. So the length of this vector is 5. I'll put a little 5 right here. That's the length of the vector from the origin to the tip. Now, let's turn our attention to the direction. What is this angle? It is the inverse tangent of the y component divided by the x component. The y is 3 and the x is 4, so 3/4. So take 3/4, 0.75, stick it in your calculator, take the inverse tangent, and you're going to get 36.87 degrees. And you always should double check, is this angle correct? This is a quadrant 1 angle. This is a quadrant 1 vector, so this does make sense for about 36 degrees, so that seems to be correct. So let's stop this, and now let's say, all right, we multiplied this vector by 10. This is the new vector we got. Now let's ask ourselves, what is the magnitude of 10 times the original vector? Well, what do? We take the square root of the x component squared plus the y component squared. And so, whoops, if I can do 10a. Well, what do I get here? What is 40 squared? Well, that's 1600. What is 30 squared? That's 900. And so, 1600 plus 900, that's 2500. We're taking the square root of this, so 10 times a. If we take the magnitude, what is the square root of 2500? You're going to get 50. So without looking at the angle at all, notice the original vector a had a length of 5, and the new vector has a length of 50. This is exactly 10 times the length. Because we took the original vector and we multiplied by 10, and we're proving to ourselves that the new vector is 10 times bigger than the old vector. Let's close the loop and say, well, what is the angle? It's the inverse tangent of y divided by x. The y component is 30, and the x component is 40. But wait a minute, this is the same thing as the inverse tangent. We can simplify this of 3/4. And so we're taking the inverse tangent of exactly the same thing, and so the angle is 36.87 degrees. Now, why did I go through this exercise? Because it's easy when vectors are lined up on the x-axis to think, okay, they're multiplied tenfold, they get 10 times bigger. If they're lined up, that was the y-axis, sorry. If we put it on the x-axis or the y-axis, multiply by tenfold or fivefold or whatever, we can easily visualize that they get stretched. But when it's on an angle direction, until we prove it to yourself, it's kind of hard for you to believe. And I told you verbally, in fact, just to remind you, I drew this and I said, if the vector is at some angle, multiply it by 4, it makes it 4 times longer at the same angle. If this is a vector and you multiply by 1/3, which is multiplying by a scalar, it makes it 1/3 of the original size, but at the same angle. Here, I'm proving it to you that this is the case. I say, here is a vector with a 4 on the x component and 3 on the y component. That's my example vector. And then this is what it looks like. And then I multiply the whole vector times 10. Because of the distributive property, it gets multiplied times each component, and here is the new vector. If we draw that vector, we can see visually that it's exactly the same angle, but we're surmising that it should be 10 times longer, but we need to prove it to ourselves. So we take the original vector, we find its length, and we find out it has a length of 5, and we figure out that this is the angle from the inverse tangent. Then we take the multiplied 10 times bigger vector, and we find its length, and we find that its length is 50, but its angle is exactly the same. So what have we shown? That if we take a vector and we multiply it by 10, we get a new vector 10 times bigger, but the angle is exactly the same. So I'm hopeful that I can prove it to you once, so you don't have to stress about it and be unsure of yourself going forward. The punchline is that any vector pointed in any direction, if you multiply by a scalar number, you maintain the orientation of the vector, the angle is the same, and you make the vector either longer if you're multiplying by something bigger than 1, or you make it shorter than the original vector if you're multiplying by a fraction something smaller than 1. But the angle is the same. And the prototype in your example of what do we use it for? Force equals mass times acceleration, because we're multiplying by a mass. So forces, which is a number, a scalar quantity. So forces and accelerations, you can almost think of them as being cousins of each other. Forces cause accelerations, as governed by this equation, but they're basically the same thing. They're just different ways of manifesting. The force is the action that causes the thing to accelerate. The acceleration is the result, but both vectors are pointed in the same direction. One is just longer or shorter than the other. That's the prototype in your example. Now, what I'd like you to do is watch this lesson twice and solve them all yourself, including this proof at the end. I think it's a good exercise. Follow me on to the next lesson. We're going to do another example to solidify this. But then as we get into the other lessons on how to multiply vectors in various ways, I'm going to try to give you that prototype example for what we call the dot product between two vectors and the cross product between two vectors. I'm going to give you that prototype for each one. The prototype for multiplying by a scalar is Newton's law. Vector multiplied by a scalar. Keep it in mind, because I want you to compare it in your mind to when we learn how to multiply vectors in other ways very, very soon. So follow me on to the next lesson, and we'll wrap up the concept of multiplying a vector times a number, which is what we call multiplying times a scalar. Learn anything at mathandscience.com.